I am going to give you a progress report on this effort that Guido mentioned in his remarks about an attempt to establish a probabilistic perspective on climate change for our region. So largely this is going to be using the latest generation of GCMs, but there's one or two examples here that fall back to the previous AR4 simulations. So just by way of refreshing, no real news here that as previous authors, Ellen just made this point that we're quite sure the global system is warming. We're quite sure that sea levels are rising, glaciers are shrinking, and the oceans are becoming more acidic. And we're quite sure that this is attributable to humans. We are uncertain, however, about a lot of the details concerning magnitudes and even the sense of some of the changes. And so, hence, the need for a view of essentially of distributions if we can form those in some way. So the uncertainties that we're talking about really fall into three or four kind of broad categories. One involves climate models and the climate sensitivity itself. So we're really still, to some extent, groping about how much warming there will be per unit of anthropogenic forcing, or even not anthropogenic forcing. And then we certainly have uncertainty in the pathway that we'll take in the following decades and so forth, as far as how much loading there will be in the atmosphere with greenhouse gases, aerosols, and even land use. And then, of course, there's natural variability, which occupies timescales of from weather to centuries. So that's to be contended with as well, and to some extent, that's really not predictable beyond the weather timescale to some extent. Finally, there's actually the response of the various systems that we're looking at and the impact. And in many ways, we haven't worked all that out with accurate knowledge. So that's another thing that we're contending with. Just to give us a reminder, these are the representative concentration pathways, essentially the radiative forcing equivalent of how the atmospheric loading will change over the future. There's a number of scenarios. Alex discussed at least three of these in his talk just a minute ago. And I guess what I would say is that currently we are focusing on the blue trace here and the red trace. That's RCP 8.5. That's the relatively high emissions pathway, and 4.5, which is relatively moderate. As Alex mentioned, the more modest scenarios are, at this point, look a little bit unrealistic. It turns out that when we were gathering models to be embroidered into the work for the at least the initial phase of this assessment 8.5 and 4.5 were the model simulations that were most available. So there's also a measure of expediency in why we've gone in that direction. This is the warm season temperature envelope, spaghetti if you like, for this is a location that you can think of over Sacramento. These have been downscaled. And the major figure here shows the 8.5 simulations from 31 models. That's the broader gray envelope, and then 10 models. The red ones are interlaced over them. The little postage stamp at the lower right is the 4.5 RCP 4.5 simulations. I guess what I would point out is that in the morning plenary, we've heard that there's a goal of trying to maintain global climate warming less than 2 Celsius, which lies a little bit below this dashed line, horizontal line on this figure. This, mind you, is the summertime warming, which is more than the cool season warming. But according to the model simulations, we have a huge challenge if we're going to avoid that. This is looking at an ensemble of simulations, in this case 32 of them, that David Pierce, my colleague, co-author on this talk, even though he doesn't know it, prepared. And this is a measure of hot days in Sacramento. So in this case, a hot day is one which exceeds the 95th percentile of June through August days here, and by definition, that happens 5% of the time. That's that dash line that goes across in the historical period for the GCMs. But what you see is that as time marches forward, depending on whether you're in the 4.5, which are the lighter pastel-y shades, or the 8.5 bolder, brighter shaded box and whiskers, we are seeing a doubling of the number of such days by about 2030, and by mid-century we're seeing something in the neighborhood of 3 to 4 times as frequent of these hot days again in mid-century. By end of century, of course, the numbers catapult even higher under the existing model. I wanted to make a point about the natural variation that occurs. Ram mentioned this in his remarks this morning, and I'm choosing here to illustrate that. There's this sea level rise issue, which, as Guido mentioned, is part of the agenda in looking at the fourth assessment. Just a little bit of a twist on this is that often we think about this natural variation in terms of decadal variability of essentially annual or interannual average conditions. But another thing that's really important is that there's multi-year variability by way of just the number of extremes. And this is the observed sea level record from Fort Point, San Francisco, in which we simply counted the number of occurrences of sea levels that occur at the historical 1 hour in approximately 14 months level of occurrence. And notably, many years never see that kind of exceedance. They don't see that sort of inundation, but a few years, of course, see a lot. And the ones that really stand out in this record are 1983 and 1998, old friends, the climatologists anyway, really large El Niños, in which case you get more storms, probably larger storms, and in 83, of course, we had a case where in late January we had really large storms on top of very high monthly tides. So this is the kind of thing, even in the future, it is probably going to affect us in terms of coastal problems. The still water levels, even if they reach that 2-meter mark, I guess that could be bad. But if there's storms and waves on top of them, then it's really bad. So that's the kind of thing that we're concerned about. This is a very incomplete ensemble, so we wouldn't consider this to reach Guido's probabilistic kind of level. But this is using a big handful of GCMs in which we've modeled the hourly sea level. That's this blue envelope. So there's a whole swarm of hours here that are projected in the future for San Francisco. The projections include not only the tides, the weather, short period climate, but also, in this case, one scenario of secular change, and that's the NRC 2012. I got the year right. Oh, thank you. Should read my own slide. Projection, so that gives you just under 1 meter of sea level rise by the end of the century. And then as you go forward, you can count extremes, you can count duration, and so on and so forth. We would like to have, using alternate ways of deriving sea level scenarios, Guido mentioned expert elicitation and perhaps other ways to fill out the envelope of potential sea level rise. Of course, one of the issues in producing probabilistic scenarios is how do you assign probabilities to any one of these scenarios? In many cases, that's one of those at this point unknowns, and so we're pretty well groping in when we get to that area. But at least we can look forward. I think I'll skip this one, which the message already got passed, and go on to this notion that in many cases decision makers are unable to cope with 30 to 60 GCMs as far as they're assessing and planning, adapting. So the Department of Water Resources, which Alyssa represents, sponsored a group to try to come up with a process and actually consummate that process in choosing a subset of GCMs that would be appropriate for water resources planning and assessing concerning climate change across a spectrum of different issues and so forth. So that's laid out in a report that just got published, and the methodology actually to some extent uses off-the-shelf technology. It calls upon the IPCC to look at the performance historically of various GCMs and replicating pretty broad-based global measures of the climate system. It has another layer of evaluation that concerns the southwestern region and how much fidelity there is in any of the climate simulations in replicating, again, historical variability over the Southwest. That was courtesy of Oregon State colleagues, David Roop in particular. And then finally, another level of evaluation that was more specific to California. And in going through this exercise, we were able to then identify, in this case, 10 models that sort of filled or were able to get through this filtering technique. And those models, I want to show you a few results from. How am I doing on time, Melissa? Okay. So this is a diagram similar to what Guido showed for the two emissions, the RCPs that I mentioned, 4.5 above, 8.5 below. This is just a simple plot of the change in temperature aligned across the horizontal axis and precipitation in percent of historical average shown in the vertical. And the models that were selected in the CCTAG, the Climate Change Technical Advisory Group exercise, are the ones that are bolded there for each of the scenarios. Guido pointed out that in conducting this process, by the way, we did not explicitly look at temperature change or precipitation change in the models to try to fill in corners of this matrix. So they just happen as they might, and this is a diagnostic. This is not one of the determining factors. I think Guido was mentioning the fact that we, in so doing, we might have missed some of the drier models. But when I look at this, this compares the 10 to a broader matrix of 31 that we had available. Those are the other light dots, or the other 21. And you see that the more or less we kind of cover the ground of the broader horse scale change, this change happening, in this case, kind of squared on Sacramento in these GCMs. So let's look a little further. This is the part of that temperature period that Alex pointed out that's really critical in terms of the snow hydrology in the Sierras, and this is a point that's just east of Sacramento. And in this case, we're looking at the 31 GCMs, and I'm showing you the median of the 31 models. That's the bold line, as well as the 80th and 20th percentiles. That's the light line, and then each dot is the extreme, or the sample of 31 models. So, of course, the red is the RCP 8.5, and the blue is 4.5. That, again, from the broader sample. This is the same, but only from the 10 GCMs, and you can really the medians anyway are very closely aligned with the broader sample. So we sort of felt that we didn't do a terrible injustice as far as looking at the core scale characteristics of the model. This shows the same thing, but now for precipitation again, just a point just east of Sacramento. And one thing to note here is the line looks horizontal because precipitation doesn't change very much over time at this location. It's, you know, my view of California precipitation in the future is continued variability and maybe a change in the distribution of precipitation within a year, but the annual totals over a long period don't change too much. And that's borne out in these simulations. There's the 10 compared to the 31. And there's more chatter when you reduce the sample to 10 because of the power of averaging. When you do 31, of course, you get a smoother line. But probably the 10 still are pretty representative. Okay. He said 5 minutes about 2 minutes ago. So you're this is I'm almost there. This is the driest decade from, in this case, just the 10 models, and each model is a couplet of these bars. Each bar is a 4.5 and an 8.5 change in precipitation from average for the driest decade in the projected future. The driest decade historically is the dark black bar for 3 representative points in California. Call it Shasta, I don't know, Yuba, and San Diego. And story here is that if we look at just east of us here today, that you know, there's variability. 8 of the 20 simulations actually have drier 21st century decades than historically. But 8 out of 20, that's kind of almost half and half. You go to Southern California, on the other hand, 14 of 20 have drier decades than today's climate historically showed. So this is showing this tendency that we've shown previously, where perhaps Southern California is on the edge of that subtropical high expansion drying that even gets worse in other Mediterranean areas or even south of the border of us. Just a couple of last slides showing we're also taking this downscaled information and running it through a hydrological model. This is the variable infiltration capacity model, or VIC, and which is a macro scale calculation that's been used for a lot of climate studies. In this case, it's been applied. Unfortunately, I don't have an update of this, but this is for CMIP3 AR4 simulation a generation ago, where we had, in this case, 16 GCMs, 2 emission scenarios, a high and a moderate one, and we're looking at the spring snowpack change in over the snow water laden area of the state. And what we see is that if you mush all these simulations together, by mid-century, we lose about 1/3 of the snowpack. By end of century, we lose about 2/3. One thing that I would note is that you don't entirely lose snowy years. That's represented by the dots at the high edge of this. But you surely lose years that, with the frequency of the days where you generate a sort of moderate snowpack, you get a lot of very low snow years increasingly over time. And there's a runoff story here where runoff in the future is about the same as today, but if you look at peak runoff, you actually see some interesting increases over time. So I think I'll forego the summing up and pass the baton.